Well, we continue in the first section of the review chapter by looking at two key ideas that have to do with sets, and that's the idea of union and intersection. So I have both defined up here. The union of sets A and B denoted, notice the kind of U-looking shape that reminds you of union. Of A union B is the set of elements that belong to set A or to set B, or they're in both sets. So that's everything that's in both sets. All the elements of A, all the elements of B, and anything common. The intersection of sets A and B denoted A, and notice it's an upside down looking U shape here. That's the intersection symbol. A intersect B is the set of elements that are common to both sets A and set B. So if there's an element in A that's not in B, it is not in the intersection. Now I have an example here, actually four little examples here that have to do with the three sets, sets A, B, and C. Find the union or intersection as indicated. Now I like to, when I'm doing sets of intervals of numbers like this, and I have the set builder notation, I like to use number lines to help me a little bit with this. And so I'm going to go ahead and I'm going to sketch out over here on the right these four different problems here. So the intersection of A and B, I'm going to draw out a number line here. I'm not going to get too fancy. And I am going to note that A is everything less than 4, B is everything greater than 2. So those are my two key values here. 2 here, 4 here. And I'm going to pick everything that is less than 4. So it would look like this. I'm just going to kind of put it above. Less than 4. Notice the parenthesis there. And everything that for B here that is greater than or equal to 2, I'm going to use the bracket here. And I'm going to write it like this. And notice there, where they overlap, that's your intersection. So you include the 2, because it's included there, and of course above, but you don't include the 4 because it's not part of this set. So we're not including the 4, but we have everything in between. It's where they overlap. So my answer to this in interval notation would be from 2, including 2 to 4, not including the 4. If I wrote this in set builder notation, and I'll do this one in set builder notation just to show you, it would be the set of all x such that 2 is less than or equal to x is less than 4, and of course x is an element of the real numbers. I prefer the interval notation for obvious reasons. Now we'll go ahead and do the union of sets A and B. Now I already have A and B drawn up here. Okay, I can use those, but notice I want everything in both. This is everything to negative infinity, everything to positive infinity. Even though they overlap, that's all part of the answer. Can you see the entire number line is used? Now that might be easier if, again, you draw it out, put down your key values here, 2 and 4. Let me get a different color pen here for this, and I want A greater, I want set A where everything is less than 4. So that would be this. Trying to put it right on the number line. Pen's not cooperating. And everything greater than or equal to 2, which would look like this. Do you see that every point on the number line is included? So this would be from negative infinity to infinity. Now to write this in set builder notation, it would just be the set of all x such that x is an element of the real numbers. All right. The union of, now we have a new set, the union of sets A and C, once again, I depend on the number line here for these interval numbers. Of course, it would help if I had a marker that would cooperate just a little bit with me. Let's try this again. There we go. My key values here would be 4 and negative 3. So I'll put the negative 3 here. I'll put the 4 here. Of course, you want them in the correct order on the number line. And for A, we're doing a union here. I want everything less than 4. Everything less than 4. We've done this a couple times now. And I want everything here less than or equal to negative 3. Less than or equal to negative 3. Now because I am looking for the union here, I want everything in both, but there's nothing out here. It goes from 4 down, not including the 4. So the union of the two sets would look like this. And it would go from negative infinity to 4, not including the 4. The last example here, B intersects C. Okay, my key value for B is 2, my key value for C is negative 3. Here's negative 3, here's 2. Okay, I want to look for everything greater than or equal to 2. That would look like this, right above it there. Everything less than or equal to negative 3, that would be right here. They don't overlap. Well, that's easy. If they don't overlap, then there is nothing common to both, and it is the empty set. And that's how you're going to approach the intersection and union of sets. Another key idea is the idea of absolute value. And we talk about absolute value usually when we're dealing with distances, but we'll start off with the definition. The absolute value of a number A is any real number, is such that if A is positive, then it's equal to itself. The absolute value of 5 is 5. Bars here representing the absolute value symbols. But if A is negative, the absolute value of A is the opposite of A. So if the opposite of a negative is positive, you see it's always a positive value because distance typically we consider as a positive value. Now we'll talk about directed distance later. So the absolute value of A is equal to itself if A is greater than or equal to 0, and it's equal to the opposite of itself if A is less than 0. So the absolute value of 5 is 5, and the absolute value of negative 5 is 5. Now it says here to evaluate each. In this case, don't grab a calculator. You should know that the square root of 5, the square root of 4 is 2, so the square root of 5 should just be a little bit bigger than 2. It's approximately 2.236068. So 7 minus that value, 2.236068, would be a positive number. So the absolute value of this would equal the number itself. On the other hand, if I switch them around, and we know that subtraction is not commutative, the square root of 5 minus 7, just looking inside the absolute value bars now, this would be a negative number. So what I want to do here is I want to take the opposite of this, because this is a negative number, so I would have this equal to the opposite of the square root of 5 minus 7, which is better known as 7 minus the square root of 5. Same values. This one's a little tricky. Students sometimes get a little mixed up with this, and it says evaluate. Well, you know why they evaluate? Because I forgot to put the absolute value bars. That would help. The absolute value of x plus 2 all over x plus 2. Well, if x is greater than negative 2, negative 1, 0, 1, 2, 3, 4, and so on, I plug those into here. This expression's positive. This expression's positive. They're the same exact expression. So this will be equal to 1. As long as x is greater than negative 2, it can't be equal to negative 2 because you can't have 0 in the denominator. If it was less than negative 2, ooh, that'd be tricky, because less than negative 2, let's say negative 3 for example. If I plug negative 3 in here, negative 3 plus 2 is negative 1, but then I take the absolute value of it, that's positive 1. Negative 3 plus 2 down here is negative 1. I have positive 1 over negative 1. It would end up being equal to negative 1 for x less than negative 2. So that's kind of an interesting idea. And as I mentioned before, we can use the absolute value with respect to distance on the number line, the distance between 2 points on our number line, A and B. Now I don't know if A is greater than B, I don't know if B is greater than A, so the distance between the two, we want it to be a positive value. So we take the difference, and again, because the difference is not commutative, we take the absolute value, because I don't know if A minus B is going to be a positive number or negative, depending on if A is bigger than B or if A is less than B. Of course, if it's equal to B, it's 0, and the absolute value of 0 is 0. Write an absolute value expression that represents the distance between negative 7 and negative 4 on the number line, then simplify. Now, when you were first given this problem, back in pre-algebra, you would put negative 7 here, you'd put negative 4 here, and you'd say 1, 2, 3. My answer is 3. But you don't have to do that, especially if you had numbers that were very big or fractions and decimals where it's not so convenient. We can use this approach right here. I can take the absolute value of negative 7 minus negative 4, or I can take the absolute value of negative 4 minus a negative 7. Either way, I'm going to get the same answer. It says then simplify. Negative 7 minus a negative 4, of course, that's the same as negative 7 plus 4 over here. That's the same as negative 4 plus 7. Negative 7 plus 4 is negative 3. This is the absolute value of negative 3, which of course is positive 3. Over here, this is equal to the absolute value of 3, which of course is 3. So you get the same answer for either problem, for either setup of the problem.